In this lesson, we're going to dive a little bit deeper into set theory. We already know how to write sets using set builder notation or by listing the elements, and we know some common sets that we're going to be working with, like the natural numbers, the integers, the rational numbers, and so on. So we're going to start talking about operations on sets. The first operation that we'll talk about is the intersection of two sets. So if A and B are sets, the intersection of A and B we'll denote by this symbol. Looks kind of like an upside down U. The intersection of A and B will be the set of all elements that are in both A and B. So if you wanted to see that in set builder notation, it would look like A intersection B is the set of all X such that X is in A and X is in B. Some examples might be if A is the set 1, 3, and 8, and B is the set -9, 22, and 3, the only number that they have in common you can see is 3, so A intersection B will be singleton 3. But maybe a more interesting example is solving a system of equations. So let's say you have the linear equation x plus y equals 7, and the linear equation x minus y equals 3. So you could think of those as each line as a set. A would be the set of ordered pairs x and y such that x plus y is equal to 7, where x and y are two real numbers. And you could have B be the set of ordered pairs x and y such that x minus y equals 3, and x and y are real numbers. So A is this line, x plus y equals 7. B represents this line, x minus y equals 3. Then A intersection B, since what we've described are two lines in the plane, is just going to be the point of intersection of those two lines. So A intersection B is going to be the set of all ordered pairs such that x and y are real numbers, x plus y equals 7, and x minus y equals 3. That's just one point, and it's the ordered pair 5, 2. So you have the singleton ordered pair 5, 2 is the solution to the system of equations, and we thought about it as the intersection of two sets. An important example is the integers intersected with the rational numbers. We already learned that the integers are a subset of the rational numbers, and so the intersection is just the set of integers itself. Or you might have two sets like 3, 5, and 9, and -5 and 8 that don't have anything in common. Then we'll say that their intersection is just the empty set. And that brings us to our next definition. Two sets are called disjoint if they have no elements in common, just like in that previous example. That is to say, A and B are disjoint if A intersection B is empty. The next operation we'll perform on sets is the union. If A and B are two sets, then the union of A and B, which we'll denote as this symbol that looks sort of like a U, the union of A and B is the set of all elements that are in A or in B or in both A and B. So in set builder notation, that is the union of A and B is the set of all x such that x is in A or x is in B. It only has to satisfy one of those things, either it's in A or it's in B. But it's important to note that if you have an element that is in A and B, then it does satisfy, so it belongs to the set. Some examples of unions: if you have the set A is equal to 2, 5, and 8, B is equal to 7, 5, and 22, since we're looking for all elements that are in A or B or both, we take 2, 5, and 8 from A, and we throw in 7 and 22 from B. We note that 5 is present in both, but we know that we only have to list an element once when we're listing the elements of a set, so we just write 5 once. We don't have to include it twice. Okay, an important example, again, we know that the integers are a subset of the rationals, so if we take the union of the integers with the rationals, we just get the rationals. That is to say that including the integers along with the rationals doesn't give us anything more. They were already there to start with. Also, any set union with the empty set is just the set we started with for the same reason. The empty set isn't really contributing anything. We don't get anything new. So A union the empty set is just A, and that is true for any set A. Now, sometimes it's helpful to establish what is called a universe. So a universe, or a universal set, is the set of all elements under discussion for possible membership in a set. And we'll usually use the letter U. So it will become a little bit more clear what I mean. Let's see this example. So if we take A to be the set of all x, such that 81x to the power 4 minus 16 is 0, then depending on where we're taking this x from, whether maybe it's an integer or a real number, then that set might be different things. So depending on the universe of which we allow our x to belong to, we'll have different sets. For example, if we only allow rational x, then the set A would just be the set 2/3 and minus 2/3. Whereas, if we allow complex numbers, then we get 2i over 3 and minus 2i over 3. So, in the context of the complex numbers, the equation 81x to the power 4 minus 16 equals 0 has 4 distinct solutions, but in the context of the rational numbers, or even the real numbers, it just has these 2 that we can find. Okay, one important thing when we're talking about set operations is using Venn diagrams to visualize these operations. It's often useful to draw the Venn diagram to help us understand the relationships. So the intersection is illustrated above. We see if we have 2 circles representing the sets A and B respectively, then wherever they overlap, which is the shaded portion here, will be the intersection of A and B. And we also have the union of A and B here. We've shaded all of A and we've shaded all of B. If we're talking about a universal set, that is usually this rectangle here. So the rectangle will usually represent the larger set U, the universal set that A and B exist within. Another operation that we can perform will be complementation of a set. And we can do complementation relative to another set or relative to the universal set. If A and B are sets, the complement of A relative to B, which we'll use the notation B minus A, is all of the elements that are in B but not in A. And if instead of B we use the universal set, then we'll denote it U minus A. That will be just generally referred to as the complement of A, and it's all of the elements that are not in A, but are in the universe. We also have a Venn diagram here. This is the complement of A relative to B. Or also denoted B minus A. So you can see that all of B is shaded except for the part that intersects with A. So here are some examples of some complements. If we have the universal set of integers 1 through 10, and the set A is 2, 4, 6, 8, and 10, the even integers, then U minus A, which is a complement, is just going to be 1, 3, 5, 7, and 9, the odd integers. Whereas A minus U is empty because U was bigger than A to start with. So if I take all of the elements in A, 2, 4, 6, 8, and 10, and then I remove any element that's in U, then I've removed everything. I'm empty. If the universal set is the real numbers, then the complement of the rational numbers is the irrational numbers. The rational numbers and the irrational numbers together form the real numbers. Okay, next we have the complement of the universal set is just empty. So when we define a universal set, we're thinking of that as everything that we're interested in. So the complement of everything is empty. The complement of empty is everything. It's the universe. We already saw the Venn diagram of B minus A. We have a Venn diagram for A complement here. So this is A complement because we have the universal set U, which is the rectangle. And we're taking everything in U that is not in A. That's A complement. And then we also have, if we do set subtraction, which was this B minus A, or we called it complementation relative to a set, then, but the set was inside, then you see what it looks like here. So B was a subset of A, and then I did A minus B. So that's this figure here. And it's important to note that we also use one other notation for set minus sometimes, which is going to be this backward slash. So depending, again, on which mathematics textbook you're reading, you might see A minus B, or you might see A slash B. They mean the same thing, and that's the complementation relative to the set. Okay? I think the last elementary operation that we'll talk about is what's called a symmetric difference. So again, we start with two sets A and B. This operation is going to be denoted with this, looks kind of like a plus sign inside of a circle. This will be A symmetric difference B. And it's the set of all elements that are in A and all the elements in B, but not in both A and B. Which is to say that the symmetric difference of A and B is A union B minus A intersection B. And we'll see the Venn diagram for that here. This is the symmetric difference. So you take everything in A and everything in B, but then you just remove that intersection in the middle. So some examples of symmetric differences are here. A is 1, 3, and 8. B is 2, 4, and 8. We want all of the elements in A and all of the elements in B, but we're removing anything that's in the intersection. The intersection, it looks like, should just be the number 8. So then the symmetric difference is 1, 2, 3, and 4. We don't include 8. All right. A symmetric difference with the empty set is just A for any set A. And for any set A symmetric difference with itself is empty. The real numbers, symmetric difference, the rational numbers, is the irrational numbers. We know from the previous lecture that the rational numbers are contained inside of the real numbers. And the symmetric difference operation is to take everything in the real numbers and everything in the rationals, but then just remove the intersection. Since the rationals are inside the real numbers, the intersection is the rational numbers. So when we remove the intersection, we're just left with the irrational numbers. Now we're ready to do some practice exercises. So the exercise here says let A equals the set 0, 2, and 3. B is the set 2 and 3. C is the set 1, 5, and 9. And we're talking about the universe that is just 0, 1, 2, and the integers up to 9. So it's asking us to find the intersection of A and B. The intersection of A and B should just be 2 and 3, because 2 and 3 are in A and 2 and 3 are in B. So that's actually B. the union of A and B, I want to take everything that's in A, so I take 0, 2, and 3. Then I want to throw in everything that's in B, but I already have everything that's in B because 2 is there, 3 is there. So the union just happens to be A. Now, for part C, I want B union A. So again, I'm going to start with everything that's in B, and then I'm going to throw in everything that's in A. Well, I already have 2 and 3 because I took B, so it's just the same set. We know that it doesn't matter which order we write these elements in. So A union B is equal to B union A. And that's not a coincidence. That's always going to be true. For part D, we're asked to find A union C. So we take everything that's in A, and we take everything that's in C, and it turns out that they don't overlap, so I just write these 6 elements one by one. And we know that it doesn't matter what order we write them in. However, you may find in your homework problems, sometimes you're asked to write them in increasing order, but in general, you don't have to. So just pay attention to the instructions on a specific problem in your homework. Okay, part E is A set minus B. So A set minus B means I take anything in A and then I remove whatever was in B. So that's just going to leave me 0. And B set minus A means I start with B and I take out anything that was in A. Well, everything that's in B is in A, so that's empty. Then I want to find the complement of A, and because it's just A complement written this way, we know that that means relative to the entire universe. So I'm going to take everything that's in the universe that's not in A. So I'm skipping 0 because 0 is in A, but I can take 1. Then I'll skip 2 and 3 because those are in A, and take everything else. The complement of A is 1, 4, 5, 6, 7, 8, and 9. And do the same thing with C. The complement of C means I'm going to take everything in the universe that's not in C. So I'm going to take 0, 1. Nope, I'm not going to take 1. I'm going to take 0. Then I'm going to take 2, 3, 4, skip 5, and take 6, 7, and 8. A intersection C is going to be the set 0, 2, 3 intersected with the set 1, 5, and 9. They don't have anything in common, so that's empty. And finally, I'm asked to find A symmetric difference, B. So I want everything that's in A along with everything in B, but then removing anything in the intersection. Well, that's just going to be 0. Because if I remove the intersection, I remove 2 and 3. All right, for our next exercise, we're going to take A, B, and C as they were in the previous exercise. So let me write them here so we remember. A is 0, 2, and 3. And B is 2 and 3. And C is 1, 5, and 9. And then we're going to throw in some new sets. We have D is equal to 3, 2, and E is equal to 2, 3, 2. We're asked to determine if these statements are true or false and why. So let's look at A. The question is A equal to B? That's false. Why is it false? Well, in order for them to be equal, they'd have to contain exactly the same elements. Whereas we have 0 belonging in A and not in B. So they can't be equal. What about B equals C? That is also false. B and C don't even have anything in common. Their intersection is empty, so they can't possibly be equal. Then we'll check, is B equal to D? So B is the set 2, 3. D is the set 3, 2. That's true. They are equal because we already know it doesn't matter which order we write our elements in. And if we want to check if two things are equal, we check that B is a subset of D and D is a subset of B. Or in other words, every element in B is in D and every element in D is in B. That's true. What about E equals D? E is the set 2, 3, 2. D is the set 3, 2. Well, that's also true because we know that the set 2, 3, 2, we could just write it as 2, 3 or 3, 2. We don't need to write the 2 twice. So I'm going to say it's true that E is equal to D because E is a subset of D and D is a subset of E. Next question, is A intersection B equal to B intersection A? So let's see. A intersection B we found it above, that was 2, 3. B intersection A, still 2, 3. They are equal. And that's also not a coincidence. It's always going to be true that A intersection B is equal to B intersection A. What about A union B? This one, I think we already found that A union B and B union A were the same. So we get to say that's true. How about A minus B and B minus A? Well, let's check it out. A minus B is going to be all of the elements in A that are not in B. So that's going to be just 0. B minus A is going to be all of the elements in B that are not in A. Well, that's going to be empty because every element of B is in A. So I say false. A minus B is not equal to B minus A because A minus B is the singleton set 0, whereas B minus A is empty. Finally, the symmetric difference, A symmetric difference B, is that equal to B symmetric difference A? A symmetric difference B means I'm going to take everything in A, 0, 2, 3, everything in B, 2, 3, but then remove the intersection, so I get 0. And B symmetric difference A means I'm going to take everything in B, which is 2, 3. I'm going to take everything in A, which is 0, 2, 3, and I'm going to remove the intersection, so I just have 0. So this is true, and again, it's not a coincidence. A symmetric difference B is equal to B symmetric difference A. The next exercise, again, we have a universe that's given to us. In this case, it's 1, 2, 3, up to 9. And in this exercise, we're asked to give examples of sets A, B, and C for which the following are true. So we have to work within the universe that we're given. So I want A intersection B intersection C to be equal to A intersection B intersection C. So let's try, let A equal maybe 1, 2, 3. and B is equal to 1, 2, and 4, and C is equal to 1, 3, and 4. Let's check if this is a good example. We have A intersection B. Well, that's equal to 1, 2, 3 intersection 1, 2, 4, so it's 1 and 2. Then A intersection B intersection C is going to be singleton 1. How about B intersection C? Well, that's 1, 2, 4 intersected with 1, 3, 4, so I have 1 and 4. Then A intersected with B intersected with C should be 1 and 4 intersected with A is just 1. So that's a good example for the first one. Then I need 3 sets A, B, and C such that A intersection B union C is equal to A intersection B union A intersection C. Let's see if the same sets work. So B union C is going to be 1, 2, and 4 from B. From C I also get 3, so I get the set 1, 2, 3, 4. Then A intersected with that set is 1, 2, and 3, all of A. What if I do A intersection B? I already know that. How about A intersection C? A intersection C should be 1 and 3. And we already know A intersection B from up here is just singleton 1. So then when I do A intersection B union A intersection C, I get 1 and 3. Rather, I get 1, 2, and 3. So I take this part here, 1 and 2, I intersect with 1 and 3, or I do the union, so I get 1, 2, and 3. So these are equal. So let's try for A union B complement. We want sets such that A complement intersects with B complement. So A union B is 1, 2, 3, 4. That means if I take the complement, and remember I'm taking the complement with respect to the universe, which is 1 through 9, the complement is going to be 5, 6, 7, 8, and 9. Now I want to check if that's equal to A complement intersection B complement, so I need to know A complement. Should be 4, 5, 6, 7, 8, and 9. B complement is 3, 5, 6, 7, 8, and 9. So when we intersect them, we get 5, 6, 7, 8, and 9. And they are equal. Then we have A union A complement equals the universe. Well, A is 1, 2, 3. So that's 1, 2, 3 union its complement, 4, 5, 6, 7, 8, and 9. And that is certainly equal to all of you. Then A is a subset of A union B. Well, A union B we know is 1, 2, 3, 4, and A is 1, 2, 3, so it's definitely true. that 1, 2, 3 is a subset of 1, 2, 3, 4. And then lastly, A intersection B is a subset of A. A intersection B is 1, 2, and it is most certainly a subset of A. So again, none of these things are coincidental. The exercise has asked you to find sets that satisfy, but these things are all true. The intersection of A with any other set is going to be a subset of A. A is going to be a subset of A union with any other set. A union its complement should definitely give you the whole universe. A union B complement is A complement, intersection B complement, and so on. So these are rules that we'll learn probably in a little more detail later. The next exercise, we have U equals 1, 2, 3 up to 9, and we want examples to illustrate the following. If A is a subset of B and B is a subset of C, then A is a subset of C. So let's take A to be singleton 9, B to be singleton, not singleton, doubleton, 8 and 9, 8, 9, and let's let C equals 7, 8, and 9. So I chose them in this way because I knew that I wanted A to be a subset of C, which I have. 9 is a subset of 7, 8, 9. And I wanted B to be a subset of C. Rather, I wanted A to be a subset of B and B to be a subset of C. So I've accomplished that, and then as you can see, the result is that A is also a subset of C. Then we want to illustrate the fact that there are sets A and B such that A minus B is not equal to B minus A. Well, let's look at the sets that we just had. If A is singleton 9, then A minus B, all of the elements in A that are not in B is empty. B minus A is all of the elements in B that are not in A. So that's not empty. There's an element there. It's 8. So you can see that it's not necessarily true that A minus B should equal B minus A. For part C, if U is the union of A and B, and Phi is the intersection of A and B, it always follows that A is U minus B. So let's take the set A to be maybe the even numbers between 1 and 9. And let's take B to be the odd numbers between 1 and 9. So we can see clearly that the union of A and B is going to be all of the numbers 1, 2, 3, 4, 5, 6, 7, 8, and 9. The intersection is empty because there are no numbers in common. And if I take the universe and I subtract B, then I will take the set 1, 2, 3, 4, 5, 6, 7, 8, 9, subtract the odd integers 1, 3, 5, 7, and 9. I'm left with exactly A. And the problem doesn't ask us to do it, but we can also notice that clearly if I subtracted A, I would get back B. So this one's A, and this one's B. What about A symmetric difference B intersection C equals A symmetric difference B intersected with A symmetric difference C? Let's look at the sets we had in part A. We had A is equal to 9, B is 8 and 9, C is 7, 8, and 9. Then B intersection C is 8 and 9. B intersected with C is 8, 9. And A symmetric difference with B intersection C then is taking everything in A, everything in B intersection C, and just removing the intersection. the intersection is the singleton 9, so we get 8. Whereas if I did asymmetric difference B, I get 8. Asymmetric difference C, I get 7 and 8. So asymmetric difference B intersected with asymmetric difference C is 8. So these sets work. Again, that's not a coincidence. Okay, here's an interesting question. What can you say about A if the universe is 1, 2, 3, 4, 5, and B is 2, 3, and it says we're going to treat these separately. So for A, the union of A and B is 1, 2, 3, and 4. The union, we know, is the set of all elements that are in A or B or both. So what we can say is that, well, 1 and 4 must belong to A because they're definitely not in B. And we can say that 5 can't belong to A. And that's about as good as we can do. We don't know about 2 and 3 because they could belong to A or they might not, since we're allowed elements that are in both. When we have the intersection of A and B is equal to 2, and remember we're doing them separately, so we're no longer assuming that A is true. We're just now assuming that B is 2, 3 and the intersection is 2, then we know that 2 must be in A because the intersection is all of the elements that are in A and B. And we know that 3 is not in A because if it was, then it would be in the intersection. But we don't know what's going on with 1, 4, and 5. They could be in A or they might not. Then the symmetric difference is 3, 4, and 5. And we know that the symmetric difference is everything in A along with everything in B, but removing the intersection. So what this basically tells us is that 3, 4, and 5 are not in the intersection. That means 3 is not in A because if 3 was in A, then it would be in the intersection. And it means 4 must be in A for it to show up in the symmetric difference, and 5 must be in A. We don't know about 2. In fact, I guess we do know. 2 is in A. Because it gets removed. That means it's in the intersection. And 1 is not in A. So it seems like the symmetric difference problem actually gave us the most information. All right, next. Suppose that U is an infinite universal set. A and B are infinite subsets of U. Answer the following questions with a brief explanation. Must a complement be finite? So I'm going to say no because we know one well-known example, which is we know that the rationals are inside of the real numbers. The rationals are infinite, the real numbers are infinite, but the complement is also infinite. The complement of the rational numbers is the irrational numbers, and there are infinitely many of them. What about should the union be infinite? Well, yes, definitely, because A is already infinite and B is already infinite. When we put them together, we're definitely getting an infinite set. But what about the intersection? The intersection doesn't have to be infinite, because if we think about the same example of the rationals inside the real numbers, we have the rationals don't intersect with the irrationals, but both are infinite subsets. So if we let A be the rationals and B be the irrationals, we can see that C does not have to be true. So 7 and 8 are going to be related, and we're going to use a Venn diagram. We have a universe that's going to be all students in a university. D is going to represent day students, M, math majors, G, graduate students. And we're going to visualize these relationships using Venn diagrams. So because we have a universal set, that's going to be this rectangle. And then I'm going to have 3 sets in particular inside the rectangle that I'm looking at, which are daytime students as opposed to evening students, math majors as opposed to non-math majors, and graduate students as opposed to non-graduate students. So evening students are any student in the universe that isn't a daytime student. So I'm going to shade my Venn diagram like this, so that what I should see is the only thing that's not shaded is the set of daytime students. That's A. I'll start with a similar diagram for B, the universe of all students of the university, the daytime students, the math majors, the graduate students. And now it's asked me to illustrate the undergraduate mathematics majors. So first of all, I know I'm in this bubble that is math majors, but I can't be a graduate student if I'm an undergraduate student. So I'm just going to work around the graduate students. And then what if I want to see non-math graduate students? So I start with the same picture. The universe, the daytime students, the math majors, the graduate students. And I want to make sure that I'm not in this math bubble, but that I am a graduate student. That should be here. And lastly, non-math undergraduate students. So they shouldn't be in the math bubble, they shouldn't be in the graduate students bubble, but we don't know whether they go in the day or not. So we're going to take everything outside of graduate students and outside of math. And that should look like that. I also get this little piece here. Okay. Now, what if we're told that there are 16,000 students in the university, 9,000 daytime students, 300 math majors, and 1,000 graduate students? We also know that the number of daytime students who are math majors is 250, 50 of whom are graduate students, and there are 95 graduate math majors. Total number of day graduate students is 700. Can we find the rest of the numbers? So let's do a little bit larger diagram here. So in total, we know that at the university we have 16,000 students. This is still graduate students, math majors, daytime students. And we're told 9,000 are daytime students. which means the total of this daytime bubble is 9,000 students. We have 300 math majors and 1,000 graduate students. Then we know that day students who are math majors is 250. So that I'm going to express as D intersected M 250. Furthermore, we're told that of those 250, 50 of them are graduate students. That's going to be D intersected M intersected with G. Then I know that there are 95 graduate math majors, so that's M intersected G is 95, and D intersected with G is 700, because I have 700 graduate students go during the day. So if I wanted to start filling this in on my diagram, I'd start here. This piece is the intersection of daytime students, math majors, and graduate students, and we know that that's 50. I know that the total intersection of daytime students with math majors is 250, so that means this should be the remaining 200 students. The total intersection of graduate students with math majors is 90, so this should be the remaining 45 graduate math majors. And similarly, the total number of daytime graduate students is 700, so this should be the remaining 650 of those. And by the same process, I can fill in the other numbers here. I have a total of 1,000 graduate students. I've already accounted for 745, so here's 255 who are graduate students, not in the day, not math majors. I know I have a total of 300 math majors, and I've already accounted for 295 of them. That means there's only 5 here that are not in the day and not graduate students. And I have a total of 9,000 daytime students, and I've accounted for 900 of them. So I have 8,100 here. I also know that I have a total of 16,000 total students at the university. So outside of these bubbles, if inside these bubbles I'm counting 9,000 plus 50 plus 255, then outside here I have what's left over. And that should help me answer my question. Evening students, that's the first question. Well, evening students should be total students at the university minus daytime students. And we already know from our Venn diagram above which portion evening students is. It's this one here in part A. What about non-mathematics majors? Well, non-mathematics majors should be all students at the university minus the number of math majors. $15,700. And undergraduates, doesn't matter if they're day or evening, so that's all students at the university minus graduate students. 15,000. Then we have day graduate non-math majors. So they need to be daytime students who are graduate. And we know that there are 700 of those, but non-mathematics majors. So we take the 700 daytime graduate students and we subtract the daytime graduate students who are math majors. So we get 650. So that's essentially this piece here. For part E, I'm looking for evening graduate students. So I'm going to take graduate students who are not daytime students. So that's graduate students minus daytime students. There are 300 of those. Evening graduate math majors. So I want non-daytime students who are graduate math majors. That should be this piece here, because they're graduate students, they're math majors, but they're not daytime students. And lastly, evening undergraduate non-mathematics majors. That's going to be this group. Not in the daytime, not a graduate student, not a math major. There are 6,695 of them. We already calculated. And that's how you would answer such a question. That looks like this is the last exercise on this lecture note.